Neuromuscular response. Muscle spindles are stretch receptors within the body of the muscle that primarily detect changes in the length of the muscles and the speed change in muscle length. When muscles lengthen and the spindles are stretched, this stretch activates the muscle spindles, which in turn sends an impulse to the spinal cord. This impulse results in the activation of more motor neurons at the spindle level that send an impulse back to the muscle. The Golgi tendon organ is a proprioceptive sensory receptor organ that sends changes in muscle tension. It lies at the origin and insertion within the tendon. The body of the organ is made up of strands of collagen that are connected at one end to the muscle fibers and at the other merge into the tendon proper. The Golgi tendon organ and muscle spindles work together reflectively to regulate muscle stiffness. When a Golgi tendon organ is stimulated, it causes its associated muscles to relax by interrupting its contraction. When a muscle is inhibited by a Golgi muscle tendon, the process is called autogenic inhibition. The function of the Golgi tendon organ can be considered opposite of the muscle spindle, which serves to produce muscle contraction. Adenosine triphosphate reduction. The body takes in chemical energy in the form of food, which is stored in the body in the form of adenosine triphosphate, ATP, which is a high energy compound that is converted into kinetic energy and used to create movement. The movement of the muscles required ATP. The muscles require continued supply of it. Skeletal muscles are powered by one compound, ATP. The body only stores ATP in small quantities in cells, but only enough to power through a few seconds of all-out exercise. So the body has to replace or resynthesize ATP on a continual basis. ATP consists of the base, which is called adenosine, and also three phosphates. It is formed by a reaction between the adenosine diphosphate, ADP molecule, and a phosphate. When the molecule of ATP is combined with water, the last phosphate group splits off and the energy is released. Aerobic energy system. The aerobic energy system is involved with exercise at low intensity and gets more important the longer the sport goes on. Only dehydration, overheating will end exercise using this system. Aerobic system energy varies according to the intensity and duration that is used for. In prolonged exercise, free fatty fuel acids are used because glycogen stores are limited. For high-intensity exercise, the system prefers glycogen as a fuel because of its duration. The electron transport chain is a series of biomechanical reactions during which free energy contains the hydrogen, which is deprived from the Krebs cycle, is released so that it can be used to resynthesize ATP. The results from the graphs and analysis. The heart rate results. For Summer and Maximus, their heart rate increased to about 20 beats per minute in the first 2 minutes of exercise in comparison to their resting heart rate. Looking at Josh's data, I would disregard the first results recorded because it shows on the graph that his heart rate decreases by about 40 beats per minute when he starts exercise, and comparing this to normative data. there would be considered an anomaly. Adam et al. States that oxygen contribution shows an initial increase, therefore meaning heart rate should increase to meet supply and demand of oxygen. I'm disregarding Josh's data because his results suggest an anomaly due to how the experiment was conducted. Comparing all the data to normative results, at 3 to 4 minutes of exercise the heart rate should plateau. We would anticipate the graph to show an initial increase in heart rate, but at 3 to 4 minutes or the heart rate should remain at the constant rate for the rest of the exercise. In connection to this, when exercise begins and then at 4 to 18 minutes their heart rate plateaus. However, Josh's heart rate keeps increasing all the way through exercise. So from 4 to 18 minutes it keeps increasing, so it doesn't show a plateau, therefore does not show steady state exercise in regards to normative data. Here's the graph created to show the comparison of the heart rate during data. In this you can see how the line at the bottom differs from the results. For O2 saturation, Summers' results plateau from the first minute until 10 minutes at the level of 99. It then decreases by 2 and 4 minutes from 10 until the 14th minute. Then there is another plateau that could increase up to 98 at the 20th minute until after the exercise is over. Josh's results have an increase of 2 from pre to the second minute. There is then a decrease at the 4th minute, then it plateaus from 6 minutes until post 2 minutes of exercise at 97. Maximus's results begin with an increase of 1 from pre to 2 minutes. It then has a decrease of 2 after another 2 minutes. From 4 to 6 minutes, it drops by another 6. There's an increase from 6 to 8 minutes. There is a plateau from 8 to 10 minutes. There is another massive drop at 14 from 10 to 12 minutes. Looking at Maximus' data, I will disregard it because there is a huge difference from other results and from normative data. I believe that he was being tested at an intensity that was too high, or there were either faulty equipment. So this would have to be measured again to give accurate results. Here's the data from the comparison of O2 saturation during exercise. For Summer and Maximus's breathing results, they had similar results. From pre to second minute, Summer's breathing went up by about 10 and then increased at a slower rate until the 8th minute. The breathing rate decreased at 16 minutes to post 2 minutes by about 10. Summers and Maximus's results are very similar from 6 minutes to 20 minutes. They both have steady increase and decrease at about the same time. Josh's results are a lot higher than other results. His results at 2 minutes is about 59 than the others. He also has a decrease sooner than the others at 10 minutes. His results increase again and they have a steady decrease from post 1 to 2 minutes. Here is the comparison of the breathing rates, which shows Josh's results a lot higher. Lactate levels in the blood results. Maximus's results have an increase of 16.2 from pre to the second minute. It then has a slower increase of 1.2 from 2 to 10 minutes, and then a decrease to 2.1 at 20 minutes. Summer's results have a slight increase in case of 12.5 from pre to the second minute. It then has an increase by 3.8 from 2 to 10 minutes. There is then a decrease of the 16th minute. Then it's an increase that I believe is an anomaly. Josh's results are showing that he could have been possibly working anaerobically. I believe this because it increases by 1.1 in the first 10 minutes, then decreases by 0.2, then increases to a further 2.4 at 20 minutes. Josh's results show very little lactic acid in the bloodstream, which could suggest that he was using another energy system. Here's the results of what happened. Josh's are at the bottom. During steady state exercise, we thought about that the anaerobic system would be the energy system that would be used most. To test this, we came up with two different ways of measuring it. We used the lactate reading as well as the O2 saturation to measure the main source of energy. We took lactic levels. By using this, we determined that the anaerobic glycolysis system was the main source of energy. Our hypothesis states that there would be low lactic levels in the blood recording, if any. To check our findings, we use an oxyometer to measure the O2 in the red blood cells. There is a low amount of O2 in the blood, and we can suggest that there is not enough oxygen in the blood, so another energy system must be in use. The evidence supports the hypothesis that an aerobic glycolysis system would be evident during steady state exercise. In our hypothesis, we predicted that the heart rate will initially increase in comparison to rest and will plateau around 3 minutes. To test this theory, we measured heart rate every minute on the oxyometer. The heart rate increased due to an increase in the demand of O2. After roughly 3 minutes, steady state was achieved. Heart rate will plateau and determine that oxygen has met. When exercise is stopped, the heart rate will decrease significantly, but not at the stage where the heart rate goes back to resting levels. Summer and Max's results show an initial increase which correlates with the normative data. However, Josh's data shows a decrease in heart rate as the exercise begins. I believe that Josh had a decrease in heart rate because he had a warm-up before the test, and his heart rate would have dropped to meet the intensity of levels. Both Summer and Maximus had a plateau in their data around 6 minutes. According to normative data, this should have occurred sooner than it did. In our hypothesis, we predicted that breathing rate will initially increase in comparison to rest. I believe that Summer's heart rate, breathing rate should plateau around 3 and 18 minutes, then have a steady decrease because exercise is stopped. But I believe that there should be some oxygen debt. To test this theory, measured breathing rate every 2 minutes. The breathing rate increased to an increase in the demand for oxygen. After roughly 6 minutes, steady state was achieved. Heart rate will plateau as the demand for oxygen has been met. When exercise is stopped, breathing rate will decrease significantly, but not to the stage where it goes back to resting levels. Summer and Max's data show an increase which correlates to normative data. However, Josh's beginning breathing rate as exercise begins. I believe that Josh's breathing rate was higher at the start due to a warm-up, and his breathing rate should have been higher. And according to normative data, it should have occurred sooner than it did.